Don't forget to print out the lab for tomorrow. We are beginning. Are you taking notes on the computer? If you haven't done the course entry assignment, please do that. You'll spend more time getting to it than it actually does taking it. And there we go. Who in here has had trig?
I'm taking trig.
Okay,
Oh.
so we got 2 in the middle of it. Most people have had it.
Well, are you talking like trig as a course or just basic trig?
Right triangle trig,
Oh,
basic SOHCAHTOA.
yeah, I know that.
We're good with that? Sort of? All right. And there are videos that I've done where I go over trig, so it's under, I think, module 0, background information or review, or however I labeled it. You know, I really should check that, but, I mean, to know what I called it. So I'm gonna go over it quickly right now, but if you need more, you can always ask or look at the videos or ask your math teacher. Maybe these will work. What is it?
Vector.
That's an arrow.
On?
Or a line, in this case.
Oh, let's nitpick this. I mean, the spirit of what you're saying is all right, but it's not a line.
Is the stop, does that have a point?
Does that have a point? Is there a point right there?
Yes,
Sure.
it's a ray.
Okay, closer. Still not a ray. Although in math class, that's how a ray would be drawn.
A direction?
Okay, could accept that. First off, why is it not a line?
Acceleration, maybe that.
No, too specific. Why is it not a line?
The line has a defined start and stop.
No, a line goes to infinity. It has to have 2 arrows on each end. Well,
Oh.
1 arrow on each end.
Or a head?
Yes.
Line segment has a defined start and stop. All right, enough of the mind reading bit. It's a representation of a ray. It's not actually a ray, it's a representation of a ray. Or in the context of this class, it's a representation of a vector. It's got a specific length, it's got a specific direction. One way of representing a vector. Now I am gonna run into this issue throughout the course, and I apologize for it now. The fact that I've got 2 151 classes. One is an 8-week class, and then there's the 16-week class. And so now I'm going through all right, I know I've done some of this, but did I do it with this group or the other group? So, what was the last thing I did last? We just did we listed some sample words that relate to vectors and scalars. We haven't done any vector addition or anything like that.
No.
Did we talk about polar notation, rectangular notation?
No.
Okay,
We just got the words.
all right. So that explains some of the reason why no one said vector right off the bat. Or perhaps I just missed it. I missed it. Okay, I apologize. All right, so there are 3 main ways of representing vectors. One way is the actual physical graphical method, where you have it as a specific length in a specific direction. Another way, so this would be the graphical, although I think graphical is the right word as opposed to graphic. There is rectangular notation. Actually, let's do polar next. Polar notation.
Graphical is an adjective, so in this case it is.
So
It's a graphical vector.
notation. Representation is probably better. Representation. Polar notation is, well, it just explicitly writes out the two factors that go along with every vector, the magnitude and the direction. So an example of polar notation would be, say, 4 newtons and 130 degrees. That is a very, just straight up size or magnitude and direction. Now, working in polar notation, although quite explicit, is not necessarily the easiest to work with. So thus, we need to use some trig. The essence of trig, as I think most of you have seen, is that if I have similar triangles, and when I say similar triangles, what do I mean by that?
They are not exactly the same, but they're probably a scale of each other.
What has to be true for them to be similar?
They have to have the same angles, not necessarily the same length of the sides.
Okay, same angles is the key. We'll be dealing with right triangle trig. Now, for those of you who have had the pre-calculus trig or some other more advanced trig than what we're going to be doing here, feel free to use it. If you need to use law of sines, law of cosines, I have no problem with that. Not necessarily the simplest approach, but if that's the way your mind is working at that moment, I guess it's the simplest for you. So if this is a 3, it's the bigger one, so let's make that the 3, 4, 5 triangle. And these are similar.
6,
Well,
8,
if that's
10,
6, this would be.
8, 10.
And so we have this ratio of sides is going to be the same for both. We have 4 is to 8, as 3 is to 6, as 5 is to 10, or 8 over 6 is the same as 4 over 3, which is more important for trig. So if I take this angle right here, that angle would be the same. And so the ratio of the opposite over the hypotenuse would be the same for both. So they came up with the shorthand of,
Sine.
let's call it something, yeah. So they called it the sine. For those less familiar with it, they saved a lot of time by dropping the E. The sine of theta is the length of the opposite side. So imagine you're in a room with 3 sides. You're standing in a corner. The opposite one is the wall that you are facing. I've had students with issues with that, but that's the way I think about it. So the sine of theta is defined as the opposite length over the hypotenuse, the long side, which in this case would be 4/5. The cosine is defined as the ratio of the adjacent side to the hypotenuse.
3/5 or 6/10.
And then the third one that we really care about,
Tangent or tan.
which is the opposite over
4 over
the
3.
adjacent. And hopefully we can decipher the handwriting.
I cannot, actually. What does it say?
It's what you just said.
Okay.
Tangent of theta is the opposite over the adjacent, or which is 4 over 3.
Is that trig notation or something, or is that just an example?
The trig notation.
Okay.
Tangent, T-A-N, short for tangent. You know, very briefly, for about 2 weeks, the board was actually raised. It was nice. But unfortunately, they lowered it. So it's a lot more difficult for me to write down here. tangent, and cosine. But as usual, we want to limit the amount of writing we have to do, so sine, cosine, tangent. There are, of course, three other, I guess, what I would consider secondary trig functions: secant, cosecant, and cotangent. We're not really going to worry about those. And then there's some hypertrig functions and so forth. Again, I don't care about those. Now, as with any solving of a problem, you're trying to isolate an unknown, but it's tacked on to the sign, so we need to somehow get the sign away from this, and so we have to do the opposite, just like with algebra. Instead of, if you're adding something, you need to get rid of it, you subtract, you do the opposite. Well, here we have to do the opposite of sine, which is
Soki?
Secant? Secant?
the wrong opposite.
Cosecant?
Actually, cosecant would be the reciprocal.
Repeat your question?
How would you undo sine? What's the opposite mathematically?
It's
I missed
just
it.
inverse it, inverse it.
When you say inverse it, what do you mean?
I mean, like, for tangent, you'd say like arctangent.
All right, there we go.
For sine.
The trouble with inverse is there's multiplicative inverse, there's additive inverse, and then there is the sort of inverse trig functions, or arc functions. So yes, too many students in the past try to get rid of sine by dividing by sine. No, you're not dividing by sine. So you do the arc function, arc sine of theta is equal to arc sine of, in our case, 4/5. The math people still insist that if I do it to one side, I have to do it to the other. Arc sine of sine, they sort of cancel out, and I'm left with theta is equal to the arc sine of 4/5.
Can't you just do sine to the -1?
And as we're getting towards that, now, most of your calculators, I suspect, do not have arc sine
They don't.
on it. Mine listed, and the way I tend to have shortened it, is a sine. That is what my calculator does. Most of yours will have the sine -1. I say most, I assume that hasn't changed. Not a fan of this notation because usually something raised to the -1 is the reciprocal, and this is not a reciprocal. To be sine to the -1 would be 1 over sine.
It's the inverse. It says that it's the inverse.
Yeah, again, the one, that is the multiplicative inverse of x.
Yes.
So the term inverse is a very general term. The inverse trig function.
But the technicalities.
Yeah, I've had enough students who just will divide by sine somehow.
Uh-huh. Okay.
And I've witnessed on camera, and I've witnessed from you, I actually can't throw some things away. All right, so you plug into your calculator, and you end up with theta. Now, this might be an issue for some of you, especially if you're in, well, it depends on which math class you're in. If you're in radians or degrees. That's probably the only two that you deal with it regularly. We tend to work in degrees until we get to near the end of the course, and then we'll switch over to radians, but we'll be dealing mainly with degrees. So just make sure your calculator's in the right one. So anyway, what is the angle? Feel free to pull out a calculator.
My calculator's dead. Can I do it on my computer?
Okay. Or if you know it off the top of your head, just shout it out.
Apparently it's 53 or something.
What's that?
Something.
.93. Anyone else have something different?
Are we doing inverse sine 4/5?
Yes.
Wait, that was in radians.
Ah.
Cause I got 53.13 degrees. Actually, it's 130.
I would take off points for that answer. Stephanie, did you say something? Laura?
Why are you taking points off?
That is a darn good question. Why would I take points off for this answer?
Doesn't have degree.
Figures?
No.
Doesn't have it doesn't have degree. It doesn't have degree thing.
There we go. If there are no units after it, it's assumed to be radians. So .93 actually is fine. You don't have to write radians. But if you don't put units down, it is assumed radians. Otherwise, you do need to put the unit down. This is physics. Units matter. Units should matter in math, but I don't think there is incentive about it as I am. All right, so we now have that angle. So let's take a vector here that represents 10 meters. And this is 53.130 degrees. In graphical form, we have just the line, the green area there. In polar form, I would write it as 10 meters, 53.130 degrees. My points should probably look like points. There we go. So this is polar form. But I can also express it as how far I go over and how far I go up. Or how far I go in one direction, how far I go in the other. So I could describe the exact same thing as, well, I traveled 6 meters to the right, and then 8 meters up. You know, I was complaining about the fact that the board is too low for me to write legibly down here, but apparently I've got that issue anywhere on the board. Now, as you might guess, that's a lot of writing. There's got to be a simpler way of doing it. Let's see, I went that one. Or not. There we go. Well, instead of to the right, if there's just a shorthand of doing that, it'd be convenient, and so let's do it. There is something known as a unit vector. Now, you can differentiate a unit vector from a regular vector by a specific notation. First, a letter to identify it, and then the hat in order to identify it as a unit vector. Now, a unit vector has a magnitude of, it's a vector, so it has to have a magnitude and direction. So the magnitude of a unit vector,
Is this a fixed thing?
One.
there we go. Yep, it's 1.
So the eye is invisible, or
It's the,
wait, no, that's wrong. That's a different question.
okay. Oh, it's not the imaginary. If that's
Okay.
what you're thinking of.
Yeah, it
No,
was.
that's different eye. All right, so it's a unit vector because I have the hat on it. It tells me it is a unit vector, so its magnitude is 1. The direction of a unit vector is what I say it is, or what you say it is, depending upon who's solving the problem. So I'm just going to say that I'm going to draw a little arrow to the right and put a little I hat right there. to indicate that I hat is the same thing as saying to the right. I could have made I hat to the left.
So I hat is, again, the magnitude?
I hat is a unit vector, has a magnitude of 1 and a direction of to the right because I said so. I could have made I
But
hat
it's
up.
not the part that's direction.
Say it again.
The arrow means direction, so the I hat is the other part of a vector?
It
The
is,
amount magnitude, whatever you say it is?
well, we're gonna use it as a shorthand so that we don't have to write out the words of to the right.
Okay, so
So,
does
So, for
the
example,
arrow
alright.
not take that case?
sorry, one more
Does the
time?
arrow not take that case?
Does the arrow not take that case?
If it just says this is to the right, the arrow is pointing to the right, why do we have the I hat? That's what I'm asking.
Because I have to define, alright, so I need to define to the right.
Okay,
So I draw an arrow to the right, now I have to give a label to this. I hat is the label I'm putting to the right this time.
Essentially an
Ah.
identifier.
Now, it's a two-dimensional problem, so I do need another dimension here, so I'm gonna say up is j hat. If we went to 3 dimensions, I think you might guess what that third dimension would be. The whole thing. There we go. We won't worry about the third dimensions yet.
How would you write this if it had different magnitudes? How would you write this if it had a magnitude more than 1?
It's not a unit vector then. All right, well, so now we need to apply these unit vectors to what I have over there. So instead of 6 meters to the right, I'm gonna write 6 meters I hat. Plus, that's the and, 8 meters j hat. So this is graphical form, polar form, rectangular form.